Hello there again. Let's do a little work energy problem here with a variable force. So what we have here is a 9 kilogram metal ball moving horizontally to the right at 1.5 meters per second. A variable horizontal force shown in the graph is applied. So you can see that graph shows how the force varies with the distance. And we want to know how fast the ball is moving after 40 meters. Well, this can be an application of work energy. So if I do a little LOL diagram where we got kinetic energy, potential gravity, potential springs, work done. Look at what our system is. Same kind of energies at the end. So at the beginning it has some kinetic, right? It's moving. It's got a little kinetic. Then there's this work done on it. So there's some positive work done at the beginning. Now, I forgot to fill out the system first. So the system is the ball and the earth. Pretty much. I'm going to leave whatever it's moving on outside. Track, don't know that it's on a track, and the force. That force is outside pushing energy in, doing work in. There is no friction, so the track doesn't really have an effect on it. I mean, it doesn't specify the friction, but the intent is that this is the only force acting on it. And we can see here it has a net force, is what that indicates. So at the end, the force is done, and we're going to have more kinetic energy, right? So this work and that kinetic energy are going to add together. So the way this would look qualitatively is the kinetic energy it has at the beginning plus the work done by that force, is it going to equal the kinetic energy it has at the end? Everything's horizontal, there's no springs. So that's what we have going on. So I can now plug in these equations and figure out things. The kinetic energy initial is 1/2 the mass times that velocity initial squared. That velocity initial will be 1.5. The work done, we got to find, that's going to be the area. I'm going to write in the word area there. So I got to figure out that area. And that'll equal the 1/2 mv final squared. All right, so what is this area? Whoop. We got a trapezoid here. So you could remember the equation for a trapezoid, or you could just do the square here in the middle. This is a width of 10 and a height of 30, so that's 300, right? 300. This is a 10 times 10, that's 100. This triangle here is a width of 10 and a height of 20, so it's 100, right? Triangle's area is 1/2 base times height. This base is 20, that height is 30, so that's 300 also, right? 1/2 of 20 is 10 times 30 is 300. So we can see here we got 600, 700, 800. That area, which is the work, is 800 joules. So when I plug these in, 1/2, my mass is 9. So 1/2, the mass is 9, plus the 800 joules, it's positive work. Whoop, v squared. So let's go back. Cut that out. So plug these numbers in. 1/2, the mass is 9, the velocity initial is 1.5 squared, then we're going to square that, plus the area, which was that work, that's 800 joules. That's going to equal 1/2. Same mass of 9, velocity final squared. So we work this all out on the left. 4.5 times 1.5 squared. Here we get 10.125 plus 800, and here we get 4.5 VF squared. So we got 810.125 divided by 4.5 is our velocity final squared. So we get a velocity final of 13.4 meters per second. There we go. Sorry about that mistake. I'll post this